Today we're talking about deductive and inductive reasoning. And so we'll start by just describing what's the difference between deductive and inductive reasoning. The difference is that inductive reasoning uses patterns to arrive at a conclusion. So you are observing the world around you, you're finding the pattern, figuring out what the pattern is, and then describing the pattern. Deductive reasoning uses facts and rules and definitions or properties to arrive at a conclusion. So deductive reasoning gathers established evidence. Inductive reasoning finds evidence through observation. And then a conjecture, another important word. A conjecture is a conclusion that is made based on observation. So if we observe a pattern through inductive reasoning, we can make a conjecture about what the rule of that pattern is. And that's what we'll be doing a lot in our practice in a minute. Now, another important facet of inductive reasoning is that it is based on conjectures that are based on patterns. And this makes it difficult to prove true because you're just observing a pattern and you have to be able to tell whether there's anything that breaks the pattern or not, and sometimes there's a lot of possibilities. But it is easier to prove false. If you can find one counterexample to the pattern, then that means that your conjecture is false. And a counterexample is an example that shows a conjecture is false. It shows that a conjecture is false. And then one final thing before we get to our examples, we're going to do the inductive reasoning steps. So the steps you follow when you are engaging in inductive reasoning. Okay, step 1. Look for a pattern. Step 2. Make a conjecture. So you see a pattern, make a conjecture, draw a conclusion based on your observations about what that pattern is. And then 3, either prove the conjecture or find a counterexample. Okay, so let's look at some visual patterns really quick and figure out what conjectures we can make about what these patterns are. So then just really quickly, We have this series of circles where the dot is kind of rotating around, so we could guess that this is where it's going to go next. Here I've got a square and then a diamond inside the square and then a square inside the diamond. So then my next one would be to have another diamond inside that square, and the pattern can continue on like that. Here I've got a triangle, and then I've got an upside down triangle inside the right side up one. And then inside each of these three right side up triangles, I've got 3 more upside down ones. And that creates 9 right side up triangles. And then inside each of those, I could put another triangle. And then it gets hard to draw, right? But we could continue the pattern by drawing another upside down triangle inside each of the 27 right side up triangles that are created there. And the pattern would continue on down that way. Now let's look at some mathematical examples, like a sequence of numbers. So let's say I have like 1, 2, 6, 24, and then it continues. What would the next one in the sequence be? To get from here to here, we could say it's adding 1, okay? But then to get from here to here, we're adding 4, and from here to here, we're adding 18. 1, 4, 18, that doesn't seem to really be a pattern. Another way we can grow numbers is by multiplying, so let's see what they might be doing there. Here we're multiplying times 2. 2 to 6 would be multiplying times 3. 6 to 24 would be multiplying times 4. So that seems like a definite pattern, right? It's growing by 1 each time. This is times 2. This is times 3. This is times 4. So then we could say that the pattern here, we can make a conjecture that we are multiplying by consecutive integers. Integers being positive whole numbers. Integers. So my next one would be, if I were to multiply by 5, 24 times 5 is 120. So that's my prediction for what the next number in the pattern would be. The product of 2 odd numbers is, okay, so make a conjecture. What would the product of 2 odd numbers give you? Product means multiplication. Now I know that anytime I add 2 odd numbers, like 1 plus 3, that's 4, or 3 plus 5, that's 8, or 11 plus 17, that's 28. So whenever I add 2 odd numbers, I get an even number. So maybe I would have a conjecture that the product of 2 odd numbers is even. Okay, then we can just test this conjecture out. 3 times 7, what is that? 21. Okay, so right away, the product of these 2 odd numbers was not an even number. So this conjecture was incorrect. It's immediately disproven by a counterexample. Let's try a few more though and see what we get. 5 times 9, that's 45. That's another odd number. 5 times 5, 2 odd number, well, the same odd number. That gives me 25, another odd number. 11 times 13. 11 times 13 is 143, another odd number. So maybe a better conjecture is the product of 2 odd numbers is odd. And then we could keep testing, right? Because there's a whole lot of odd numbers, and all we need is one counterexample to prove this false. But it seems that 2 odd numbers, if you multiply them together, are going to give you an odd number. All right, one more example. So we're going to try to show conjectures are false by finding a counterexample here. So all odd numbers are prime. True or false? Okay, well, first of all, what's an odd number? Okay, those are the non-even numbers, 1, 3, 5, 7, 9. Prime numbers are numbers that can only be divided by 1 and by themselves. So for example, 17 is a prime number because you can't divide 17 by anything except for 17 and 1. Another odd prime number is 3. You can only divide 3 by 3 and by 1, so it's prime. These are both odd numbers, so maybe all odd numbers are prime. Are there any odd numbers that are not prime numbers? Well, what about 9? We can divide 9 by 9, and we can divide by 1. Are there any numbers I can divide 9 by? Yes, I can divide it by 3. So 9 can be arrived at by doing 3 times 3. So that's my counterexample. Also another one, 21 is an odd number. 21 you can get there by 3 times 7. So those are both factors of 21. They're not 1 or itself. So these are not prime numbers, but they are odd. So no, all odd numbers are not prime. And these are both counterexamples showing that this conjecture is false.